Okay, we need to talk about a slightly esoteric convention that's used in electrical engineering all the time, and that's the use of the word decibels. So, I'm sure you all know what the prefix deci means. It means a tenth of something, but the question is a tenth of what? And it apparently is a tenth of a bell. And we'll talk about the specific definition in a second, but who was the bell named for? Think about that for a second. You have an idea who it might be? Of course, it was named for Alexander Graham Bell. Well, the definition of a decibel scale, what it, not going into the details, but what it means is that you express a value logarithmically relative to a reference. So to see how that works, here's the explicit definition of power of a signal S in decibels. So we've got our signal S and it has some power. There's a reference signal S0 and we compute its power. It could be a standard like it's a 1 watt signal or a 1 milliwatt signal, any kind of standard reference value that is convenient for your application. You take the ratio between the two, evaluate the log base 10 of that ratio and multiply by 10. The 10 is the deci part. And that is the definition of the power of a signal expressed in decibels. Now this second definition down here for specifying the amplitude of a signal in decibels is different. Notice that it's 20 sitting out here, but it turns out that 20 is there because it's consistent with our relationship between power and amplitude. Because power is proportional to amplitude squared, if you insert this formula up into the first definition, you get amplitude squared divided by the amplitude squared of the reference. Those squares, because of the log, come out and multiply and give you a 20 log 10 amplitude of the ratio. So these are just different ways of thinking about the same thing. You can express the power of a signal in decibels, or you can express its amplitude in decibels. And the main reason why we use decibels is because adding decibel values corresponds to multiplying either power or amplitude values, right? Because the log of A times B, that's equal to the log of A plus the log of B. And this has to do with transfer functions. We know that when you put systems in cascade, their transfer functions multiply. And so you can talk about what the overall transfer function is in decibels by just adding the transfer function of each expressed in decibels. Well, let's go over some interesting values for decibels that come up all the time. This is something everybody remembers. So clearly, if the power ratio is 1, that is equivalent to 0 dB. If that power ratio was a signal to noise ratio, signal power divided by a reference noise power, 0 dB means there's just as much power in the signal as there is in the noise. And that's not good. That's a very low signal to noise ratio. If the power ratio is 10, well, that turns out to correspond to 10 dB. If the power ratio is a tenth, the signal power is 1/10 that of the reference, that's minus 10 dB. And of course, the log of 1 over x is the negative of the log of x. So that explains the minus sign. And here it is, if you multiply two things together, well, their decibel values add. So that's 10 plus 10 gives you 20. Now what's interesting is that when the power ratio of 2 occurs, that corresponds almost exactly to 3 dB. That turns out to be very, very close approximation. So it turns out to be a very important one to memorize, that 3 dB corresponds to a factor of 2. Now, how do you get this? That a power ratio of 5 has to be 7 dB. Think about that for a second. How do you get that? And the answer, of course, is that 2 times 5 is 10. Well, since they multiply here, they add here, and the sum has to be 10, because we've already seen that 10 is 10 dB. So right away, you can derive other decibel values from other ones by using the properties of the log. And then finally, I want to mention a very interesting and important one. 2 to the 10th power is just about 1,000. The log base 10 of 1,000 is 3, which makes its decibel value very close to 30 dB. It turns out to be more exactly 30.1 dB. But you can roughly say that if you have a power ratio of 2 to the 10th, that's about 30 dB. That's going to be very, very important to remember as we go on. So that's all there is to decibels. It's a very important thing we use in electrical engineering to summarize how systems work and how they are behaving. Once you get used to it, you'll use it all the time too.